Our next topic is going to be binary search along with ternary search. And I know many of you have not particularly heard of ternary search before, but it's just a simple variation, along with, I guess you would say, divide and conquer more generally. So many of you know binary search because it's one of the very first things that you learn in an early data structures class, or even before that, potentially when you're programming, as a way of simplifying a computation when you're searching through an array. But the idea of binary search is actually much more general, and you can apply it to a much wider range of problems. And so I want to talk a little bit about some of that. Now, binary search falls into this category of what we would call divide and conquer problems. So when we talk about divide and conquer, there's lots of things that you've seen before that fall in this category. So you're familiar with binary search. I mean, you've run into that before. And you probably learned things like, a merge sort, or all sorts of variations on things like merge sort, quick sort, and that sort of stuff. Anytime that that you do something that is a tree, trees are usually thought of as a way of dealing with divide and conquer, because you take whatever's at the root and you divide it into n children, all those in different parts. And there's a whole bunch of other specialized algorithms besides those. Now, the basic idea in all of these cases is that you have a large problem that might take some amount of time to solve, and you divide it into smaller things that are each one on its own maybe takes less time, and then you merge those things back together. So you'll divide things into a smaller problem or smaller problems, and solve those. And so the idea here is usually that solving the n subproblems, and n could be one, and could be it could be n, will take less time overall. Okay, so that's the idea of divide and conquer. So you might have something, for instance, if you've got an n squared algorithm, then if you divide it into two things that each take half the time, and you can solve those individually. So let's say that you've got n things, and this would normally take n squared time. Well, if I were able to divide it into two things, and each one takes n over 2 time, and even if I still use an n squared algorithm on each one of them, I end up getting 2 times n squared over 4, which is just n squared over 2. So I've actually cut my time in half by doing that. Notice that I still have an n squared algorithm. Now, it's not always possible to do this, of course. You can't always subdivide two problems, and sometimes the process of merging things back together takes longer, but very often, after you've subdivided this into two easier problems, then merging it back together might only take time n or something, which is certainly less than the n squared over 2. And so overall, it's a simpler process. Well, the basic idea of binary search is not one where you have two problems or n problems there, but you're going to take some problem that's of size n, and you're going to move it into something that's size, say, n over 2, and you keep doing this over and over. And basically, this means that you take things that are order n, and you move them into things that are order of log n. And that reduction right there, taking something that's order n to log n, remember log grows much, much slower than n. And so you can almost think of it as you remove an entire factor of n from the process. In fact, sometimes you'll see analyses done where people just ignore all the log n factors in the analysis. They only care about the n part as far as what's polynomial. Okay, so the idea of binary search can actually take a few different forms. But when we do this, there is going to be some range of values to search over. And this range of values could come in a few different ways. So the way that you typically think of this is these might be things like indices of an array of some sort, you know, a vector or a list, but there's some sort of indices. And so you're looking through some giant list, and the range that you're searching for is the first index to the last index. But it doesn't have to be indices of an array. It could be just any set of discrete values. So it might not be connected to an array at all. It just might mean that you want to find things between some value A and B, and you want to find integer values. And it could be even any range of continuous values. So they don't even have to be discrete. So again, you say, I want to find some value that's somewhere between A and B. And this is the more general form of binary search. Now, often you will see this, you'll sometimes see this called, when you're doing this over continuous values, you'll sometimes see it called bisection. And the idea is that you are creating two sections, one that you throw away, one that you keep. But the idea is you've bisected your range into two smaller parts, and you're going to find it. Now, I'm going to focus for a minute on this kind of continuous value idea, even though it's not the only way to do things. It kind of gives an idea of how all of these tend to work. The idea of having a range of continuous values and wanting to find something is that you generally want to find something that you would call a root. Okay, so you will sometimes see binary search referred to as a root finding approach. And the idea is that you have a transverse value of 0, or transverse crossing of 0 in a monotonic function. So what does this mean? Okay, what that means, a monotonic function is something that's always either the same or decreasing, or it's always the same and increasing. It never is you're never going to have something that like dips down. Okay, so this last one is not monotonic. Each of the other two, these are monotonic. So those are good things. And the idea here is there's going to be some 0 value in the function, and you want to find where is that point where something crosses the 0 value. And what that means, why that's important, is because we should be able to evaluate any point along this range right here and say, is that point above or below? In other words, is the value of the function positive or negative? Now, even if you do something that's one of these other cases, like indices of an array or discrete values or things like that, that's still the check you're doing. If you're trying to find an element of an array, then basically you're wanting to say, am I above the thing I care about, or am I below the thing I care about? Okay, so, to remind you, the general binary search that you've run into is, pick a number from 1 to 100, and you keep hearing high or low. And so you say 50, and you say, well, that's high. And you say 25, still high. And then you say 12, well, that's low. And then you go halfway, and eventually you hone in on some number that you want to. And every time you've reduced your overall size to 1/2 of that. Well, notice that when you're doing high or low, if X is the target number that you want, and G is the guess, you're actually looking for something that's X minus G, and you're saying, is that positive or negative? Okay, so if X minus G is positive, it means you're low. If X minus G is negative, it means you're too high. And if X minus G is equal to 0, you've exactly found the thing you care about. That's the thing you want. So even something like finding a particular number in a sorted array is still finding a root. It's finding where some value is 0. Okay, but think about this. If you think of a binary search problem in general, you're wanting to think, I've got some function. The function is either always decreasing or it's always increasing. It has to be one of those two things. And I'm wanting to find where that 0 is. I'm wanting to find where this crossing is, or you can think of it more generally, I'm wanting to find where a particular value is hit. And so that should only happen at one point, or maybe it happens over a range of points, because you could have something that is like this, and potentially there's a range of points, but you can always check, I'm either I've either got a value that's above, or I've got a value that's below, or I've got a value that's exactly the thing I'm looking for. Okay, so if you're doing this with continuous values, you continue this until you're always going to maintain a low, and you're going to maintain a high value. And as you go, you start out with low at the lowest thing you know you have, and high at the highest, and you always pick a value in the middle. And then either you move the low up there, or you move the high down to that point. Okay, so let's say that we moved the high down. Well, then we pick the new point in the middle of that, and we choose which one do we want. Well, let's say we move the low up. Okay, and then we take halfway through, maybe the low goes up again. Halfway from there, maybe the high goes down. And so now we've already narrowed it down to this little region right in here. And we could keep doing this until those two things are as close as possible. Now, if we have discrete values, eventually the difference between high and low will be no bigger than 1. And once it's no bigger than 1, you have your answer, because if either one of them is equal to the value you want, or one is above and one is below, and the value just doesn't exist. If it's a continuous thing, then high and low, you just subtract high and low and see what the difference between them is. So you would say, you would do something like, while high minus low is greater than some tolerance. And once the tolerance is low enough, you set the tolerance really low, like 0.0001, then you would have the result. Okay, so this might all sound kind of abstract at this point. Let's give an example that is the sort of thing that you might run into. And this is an example. If you go to the Caddis system, there is a problem. It was a former ICPC World Finals problem. The name of it was cutting cheese. And I will let you look at that one if you want to. And it's a 3D problem, but I'm going to give a simple 2D example to show you how this type of thing would work. And so the idea of cutting cheese is that you have some block of cheese. Let's say it's 2D, and it's going to be Swiss cheese. And this block has holes in it, and those holes can be various sizes and various radii. And you know the position of each hole, and you know the radius of each hole. And none of the holes touch each other. And what you want to do is you want to take that block of cheese, and you want to figure out, where do I want to cut this so that the amount of cheese, let's just say, has 4 equal parts. Okay, and if you cut it, if you just say, I'm going to cut 1/4 of the way here, well, that doesn't necessarily work, because like if you look at this example, there's a whole lot of cheese in this area, and over on this side over here, there's a whole lot of holes, and so there's not as much cheese. If you want the same amount of cheese, the same volume of cheese, you need to figure out where to set these cut points. And so the way you would approach a problem like this is you could first of all compute the total volume of the rectangle, okay, and then subtract off the volumes of all of the circles. Okay, so all of the spheres in 3D, or all of the circles here in 2D. And this is going to give you the total volume of cheese. Okay. And now if I want to find, say, like again, say I wanted to cut it into 4 parts. So I would want to find out, where is the 1/4 volume mark? Okay, so let's just to pick a value here. Let's say that this number came out to be 1,000. Well, then 1/4 of the volume would be 250. Okay, so maybe this number up here was 1,500, and the volumes of all of those was 500. So that means there was 1,000 units either of area or volume of cheese. So 1/4 of that is 250. And so now I want to say, where do I cut this cheese? At what point along this range do I cut it so that whatever I have here is 1/4 the amount? I want to get exactly 1/4 of it. Okay, so that, if you tried to do this as just a basic mathematical problem, that's very tricky. You're trying, I'm not sure there's a very easy way to do it, but with binary search, it's actually relatively easy. And so the idea of binary search is you say, okay, I have some value that I know is low. I know that this value here at 0 could not possibly be the place to cut it. And I know that this value all the way over here, let's just say that this is, I'll say it's 0.150, just to pick a number. Okay, so maybe it's 0.150. I know that that's too high. I don't want to cut it all the way over there. So I have some value I know is too low and some value that I know is too high. And so what I want to do is I want to find where is the number just right. Where do I get to 250? So I start out by picking a point in the middle. I pick, in this case, the 0.75. Okay, so if I make a cut at 75, what I can do is I can look at the block of cheese and I can calculate how much is the volume on the left side and how much is the volume on the right side. And to find the volume, I'm going to do the same thing as before. I'm going to calculate the area of the square and I'm going to subtract off the areas of the circles. Now, it does get a little tricky. I'll do an example of this in a second, because what if the line cuts one of the circles? Well, you do have to account for the partial area of a circle. You have to be able to account for that. Okay, but in this case, I might calculate that. I might say, well, at this cut of 75, this maybe came out to have a total of I'll say 600 was how much was in this region. Okay, so if I calculate the amount in that region, I got 600. Well, that's too much. I'm looking to try to get 250. Okay, so what that means is this is now going to be my new high value. I move my high value from 150 down to 75. Okay, so the next round, I pick a new value. I pick one here at 37.5. And now I cut through there. So here's my standard cut, and I want to measure what is this volume over there from 0 to 37.5. And so I would calculate the area of the rectangle and I would subtract off this partial circle here. Okay, so I'd have to actually get the area of a partial circle, or in 3D, a partial sphere. There's a few ways you can do that. It's actually not that complicated of a formula, but you probably don't have it off the top of your head. But I might do that and I might say, okay, this point right now, this comes out to have area 300. And that's still a little bit too high. So I would move my top one down from there. Then I would go to the halfway point from there. So whatever half of that is, I think it's 18.75. Okay, so I would check out 18.75, and I might compute a cut there and see how much that range is, and maybe that comes out to be, I don't know, 175. Well, 175 is too small, so now I move my low value up. And as you can see, I'm going to gradually hone in to where that quarter point is. And once I find what that quarter point is, I would always just, it'll be somewhere in here. I'd say, well, that's going to be the position where I make my cut to get a quarter of the cheese. Okay, so the point here is that what we have to do is we have to keep track of a low value, we have to keep track of a high value, and then we have some function to determine if we are above or below the target. And the target, you can think of it as the 0. Okay, so these are the things we need. You keep track of a low value, something you know is too low. You keep track of a high value that you know is too high. And then you have a function to determine if you're above or below the target. And this function can be very complicated. This does not have to be a very simple function. In fact, this might be something where you have to actually run a big algorithm to compute it. It's not just like an equation that you plug in a value for. When you have equations, things are very easy. The way you learn about root finding, you're usually just using a polynomial. In these computer science problems where you use binary search, this could be a complicated function like, what's the volume of cheese from 0 up to my cut point? That's not a simple thing to do. And there's all sorts of things that you could do here. There's problems like with a graph, and it might say, well, what edge size do you need? Like what edge weight do you need to make something happen? Well, that might be really difficult to prove, but you might be able to say, well, I know such and such a weight edge is too low, and I know that such and such an edge weight is certainly easily high enough. And if I'm given a particular edge weight, I can evaluate and see if that works. And so you can keep doing that until you find what the smallest edge weight that you need is in that graph, as an example. Okay, so there are a whole bunch of cases like that. The binary search cases, again, the idea is find something that you know is too low, find something that you know is too high, and then find a function that you can use to determine is it too high or too low. And at that point, then binary search becomes a relatively easy thing. Okay, so let me go on and talk about the next topic, which is ternary search. So ternary search is it's a little bit different than binary search. It is not designed for something that's monotonic. So remember that with binary search, you had something that was continuously increasing or it was continuously decreasing. Well, with ternary search, you're going to have something that has a single maximum or a single minimum. Okay, so you have some function that's going to increase monotonically to a point, and then it's going to decrease monotonically. So it's never going to go up and down. And you want to find what is that maximum point, and you want to do that as fast as possible. Okay, so as opposed to binary search, where you have beginning and end, and you always go to the middle and search for it, you can think of in a case like this, you can't exactly do that, right? If this is my low value and this is my high value, and I have something in the middle, I don't know, that value happens to be the same as that one there. I don't know which side of those things to keep or anything of that. I need to actually be able to determine which part to keep. So the idea here is that you keep, just like before, a low and a high, but we are going to now generate two values in the middle. So we will generate And so with binary search, remember, the number that you want is high plus low over 2, halfway in between them. So for the ternary search, instead of doing that, you're going to have, the way to think of it is low plus minus low over 3, and low plus high minus low times 2 over 3. In other words, 1/3 of the way and 2/3 of the way. So if I've got my example that I showed before, and the whole thing can be done if you're looking for a minimum also. You have to know, are you looking for a maximum or a minimum? So I've got my low and my high value. I'm going to generate 1/3 and 2/3 like that. Okay. So once you've generated your new values, let's call this one here, we'll call it A, and we'll call this one B. So here in the graph, we have A, we have B, we have low, and we have high. Okay, so we have the value at A, the value at B, the low and the high value. So we can evaluate possibly some very complicated function. It kind of doesn't matter how complicated it is to find what A is and to find what B is, or to find what the values at A and B are. Okay, so now that we've evaluated this, what we can say is if the value at A is greater than the value at B, then we can set high to B. Okay, so let's look at this example. If this is like this, so pretend that's the line. So notice the value at B is below the value at A. So the value at A is greater than the value at B. What that means is I'm going to move high to B. Okay, and likewise, if the value at B is greater than the value at A, and I wrote this in 2 different ways, so let me just be consistent. Then we will set the low to to be A. So in that case, we would move the low value up to A. Okay, and the result of this is that each iteration we narrow the range by 1/3. Okay, so basically if S is the size at one iteration at size I, it becomes 2/3 of S. 2/3 of S sub I is the size at I plus 1. Okay, so each iteration is what you're left with is 2/3 the size of the previous one. And so this still leads to a log result. Okay, so it's still a logarithmic number of queries that you need. Instead of being log base 2, it's basically log base 3/2. So it is more, you have to take more steps, but it's still a logarithmic number. It still grows way, 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 way smaller than you would have otherwise. Okay, so that's the general idea. Let me just show you why this works, what this means. What we're saying is if the value at A is greater than the value at B, remember there's going to be some maximum somewhere. We don't know where it is. We've got some low values at the low and high. We know that both of those are low, and there's some value, again, we don't know where this is. There's some value there, and it's higher than that value there. So what that's going to tell me is the maximum that I have has to be somewhere in that region, because notice, we know, because this thing is monotonically increasing, we know that this section has to be decreasing. Okay, there can't possibly be, like you couldn't have something higher over here, because to do that, we would have had to have gone up and then down and then up. And that's not allowed. You're not allowed to go like that. So you know that this last part has to be monotonically decreasing, so you can chop off that last section. We can move our high point back. Okay, and likewise, if instead we had something where you have your low value and your high value, and you evaluate something in the middle, maybe that one's here and this one's here, and you evaluate something in the middle, and the one on the right is higher, we'll notice that that means that we can get rid of this section up in here. It has to be monotonically increasing. I mean, it might go like that, it might go like that, but it's not going to have the overall maximum. The overall maximum has to instead be somewhere in this range, because if it were somewhere over here, then what that would mean is we'd go from a low value up and down and up, and that's not allowed. You're only allowed to go and have sort of one local maximum. Okay, so if you have a case like this where you are looking for a maximum and your problem looks that way, then you can use a ternary search. This is the way, remember, this is the way to find the maximum. Okay, so that's how that works. So let me just mention a couple of variations, and I'm not going to do this. I'm not going to do this too much because it can, I don't want to beat a dead horse here, but there are some more general ways that you can use divide and conquer. So I will show you a couple of other ways that divide and conquer gets used to solve some problems. So one of them, it's one of my favorite types of things to look at, is what are called spatial subdivisions. And if you subdivisions, okay, so if you take a computer graphics class, you will probably learn some spatial subdivisions along the way. So things that you might hear about are BSP tree. And this stands for binary space partition. You might hear something about a quad tree or an octree. Okay, those are all examples of spatial subdivisions. And the idea here is if I've got some big space and I want to calculate something like, maybe I want to know what area is occupied by a certain thing. Well, there's different ways you could do it. So there's one example I remember seeing this, I actually wrote a contest that had this problem, and then believe it or not, it came up on a regional contest later. Imagine that you have a bunch of circles of varying radii, and they might overlap each other. They might overlap each other a lot or a little or whatever. And I want to calculate what area is not occupied by those circles. What area in this thing is not occupied by those circles. So imagine that the circles are tree canopies, and you want to say which part of the scene is getting sunlight without shade from the tree, from these tree canopies. Okay. Well, that could be a pretty difficult problem. If you were to try to take this and actually calculate exactly what the approach would be, that would be like if you were actually trying to calculate all the geometry of these and exactly what the area of each of these shapes is, that could get very, very complicated, although it is possible to do. Instead, you can use one of these things like a quad tree. And the idea of a quad tree is I can take my region and I can divide it up into different parts. And each of those parts might be entirely filled. Okay, so like this part over here has no circles in it. So I know the area of that very easily. And there's other areas that might be completely covered by circles, and there's other areas that might be just partially covered by circles. So in this case, I was able to find the area for that quarter, and I'm left with 3 more pieces. And each of those is partially covered. It's not fully covered by a circle, by any single circle, and it's not totally empty of circles. And so next I would divide each of those regions into 4, like this one. Okay, and I might, just to kind of illustrate one of these, I might take this region up here and divide it because it was partial. And notice that this part here is entirely inside a circle. Okay, so I know that that's the whole region that I don't want. All the other ones are only partially in and partially out. Well, the more I divide this up, you can see pretty quickly you're going to have regions that are entirely clear. Okay, and you're going to have regions that have to be subdivided a little bit more. And you can keep subdividing and calculate all the areas that you know are clear and calculate all the areas that you know are filled with tree coverage. And what you're left with then is you'll have an upper bound on how much open space there is, and you'll have a lower bound on how much open space there is. And the more of this you do, the finer you subdivide your regions, the closer those two numbers will get together. You'll either have something that you say, oh, I know this was filled in with trees, so I can lower my upper bound by that much. Or you say, oh, I've got a region that I know is completely open, and so I can change my lower bound. I can move it up by that much. And so gradually your lower and your upper are going to get close together and converge to the value that you care about. Okay, that's the quad tree idea. The octree is the same thing in 3D, and the BSP tree is something like that, but you only make one slice at a time, and you can use that in an arbitrary number of dimensions. Okay, another example of how divide and conquer. So you can hopefully see that that's a divide and conquer problem. I took a big complicated thing and I keep subdividing it, and eventually I get down to the only thing I care about is an entire box inside a circle or outside a circle. And it's inside a circle if the distance to every one of the points is within the circle. Okay, you can then clearly say that box is inside the circle. And if all of the points, you actually have to calculate it's a little trickier to say it's totally outside the circle, because you could have, if I had a circle like this and I had a box like that, I could say all 4 vertices are outside, but it's actually still overlapping. So you do have to be a little bit careful about it, but that's actually not a very, you can make that check pretty easily too. Okay, so that's one example of divide and conquer. Another way that you can see an example of divide and conquer is, say you need to compute a gigantic power of something. So you want to compute something like, x to the n. And now imagine n is huge. Now, one way of doing that is you could calculate x, and you could multiply times x, and you could multiply times x, and you could do that n different times. But that might take too long, especially if x might not just be a single number, it might be like a matrix. Okay, and actually computing all of those matrices multiplied together would take just too long, because each single multiplication might be a lot. Well, we can actually subdivide this problem. X to the n is the same as x to the n over 2 times x to the n over 2. Okay, and so now we've got a problem that's simpler, and we just get that, and then we square it. Okay, and to calculate x of n over 2, well, we divide that into xn over 4 times xn over 4. And so eventually you can kind of work your way down to where you don't have to compute very much at all. Now, if we assume that n is a power like integer, which it usually is, there are some times that you might need to divide this into x times x to the n over 2 times x to the n over 2. Okay, so for instance, if n was 5, it would be x times x squared times x squared. So if it's odd, basically if the exponent is odd, you might need to collect an extra x along the way. But the point is, if you do this calculation, you can turn this into, instead of having to do n multiplies like you do there, you can do log n multiplies. And that is a clear time savings that you can get, is if you ever have to compute something by doing some complicated operation over and over and over and over, and you're doing it n times, well, as long as it works kind of like multiplication, where you get the, where associativity holds. So as long as you keep doing it in the same order, as long as that's the case, you can divide this into two simpler problems and solve it more easily that way. Okay, so that is the overview of binary search. Remember, binary search applies to a very broad category of problems, anything where you can have a high and a low and evaluate things in between. Okay, so binary was high, low, and a way to evaluate a value. As long as you have that and it's monotonic, you're going to be able to do binary search. Remember, we had ternary search. So ternary search, this is where you're looking for a max and a min. And this is where you will have a high and a low. And you will create new tests at the 1/3 and 2/3 marks. Okay, so at 1/3 and 2/3, and then you'll basically keep 2 of the 3 regions that are left. Will stay at each step. And then more general, remember that you can use this idea of divide and conquer for things like spatial subdivision or things like computing powers of a number in order to take very complicated problems and simplify them down into a set of much simpler problems that you can solve more easily. Okay.